This carbon atom has flipped its orientation in both dimensions. Hey OChemNinjas! As you move through organic chemistry, rotating and manipulating molecules in three-dimensional space is a very important skill to learn. This video will cover a very high ninja level method for rotating and manipulating molecules. I call it the arrow shift method. I invented it. You probably won't find it in your textbook, but it's a really nice way to take a long molecule and rotate it into whatever orientation you want. This video follows after some lower ninja level manipulations. If you haven't already, you should start with the pancake flip and steering wheel rotations. I have links to those videos down below. A little bit higher in ninja level is 120 and 180 degree bond rotations. I also have links to that video down below. The arrow shift method is a higher ninja level still, and it combines elements of both the steering wheel and pancake flip and 120 and 180 degree bond rotations, all to get our molecule in the new orientation. I call it the arrow shift method because we're going to treat each carbon like the point of an arrow, and we're going to watch how that arrow shifts from the original molecule into the new perspective. Remember, when we rotate and manipulate molecules, we are not allowed to change the molecule. The only thing that's allowed to change is our perspective of the molecule. Each carbon atom in this molecule has a very specific three-dimensional orientation, and when that molecule rotates and manipulates into this new orientation, will those groups on wedges switch to dashes, or dashes switch to wedges, or will they stay in their original orientation? If we're only tracking one or two stereocenters, it's not that difficult to use some of the other manipulation methods. But when the molecule is more complicated, or when there are multiple of these three-dimensional carbons to account for, the arrow shift method will help make sure that every carbon gets the right orientation every time. To use the arrow shift method, we treat each carbon like the point of an arrow. We look at carbon number 2, and we treat it like the point of an arrow where 1, 2, and 3 form the point of this arrow with carbon 2 at the apex. We analyze this arrow in 2 dimensions in the original molecule, and we see how that changes in the new molecule. First, we look at the left to right orientation of the arrow. We look at the carbon numbers. Do the carbon numbers traverse left to right or right to left? In this example, carbon 1, 2, and 3 go left to right, so this is a left to right arrow for carbon number 2. Second, we look at whether that arrow is an arrow pointed up or an arrow pointed down. For carbon number 2, that arrow is pointed up, so we look at the arrow in both the left to right dimension and the up and down dimension. Then we look at carbon number 2 in the new molecule. Is that carbon going left to right or right to left, and is it pointed up or pointed down? If either one of the original dimensions changes, that's like a 180 degree pancake flip of the molecule, and that would change the wedge to a dash and the dash to the wedge. If there are no changes in either dimension, then we're just sliding that carbon over and there's no change in the wedge and dash orientation. If both of these dimensions change, that would be like a 180 degree flip followed by another 180 degree flip, orienting the molecule back in its original orientation. Looking at carbon number 2 in the new molecule, it is an arrow going left to right, and it is an arrow pointed down. Comparing the original molecule, the left to right orientation is the same, but the carbon number 2 started as an up arrow, and now it is a down arrow. That's as if we took carbon number 2 and did a pancake flip, moving it into the new molecule. That's going to take our group that's on a wedge, and when we flip it around, is going to be on a dash. So this OH group on carbon number 2 will end up on a dash because one of these dimensions changed in our new molecule. If we look at carbon number 3, we draw in our arrow for carbon number 3. The 2, 3, 4 carbons are also going left to right, and that carbon number 3 arrow is an arrow that's pointed down. When we look at carbon number 3 in the new molecule, this 2, 3, 4 goes left to right, and it's also an arrow pointed down. Yes, I know it's kind of pointed off to the right, but it's still pointed down into the southern hemisphere of this molecule. So the carbon started out left to right pointed down, and it ends left to right also pointed down. This molecule had no changes in either dimension at carbon number 3, so the bromine will still be on a dash in the new orientation. From the perspective of carbon number 3, all we've really done is rotate it a little bit like a steering wheel to get it in position in the new molecule. For carbon number 4, the 3, 4, 5 numbers go left to right, and this is an arrow pointed up. When we look at the new orientation, the arrows for 3, 4, 5, this 3, 4, 5 goes right to left and is an arrow pointed up. One of the dimensions has changed from the original molecule to the new molecule. That would be like doing a pancake flip on carbon number 4. So that methyl group that is on the dash is going to flip and now be on a wedge in our new orientation. For carbon number 5, the 4, 5, 6 group goes left to right, and this is an arrow pointed down. In our new perspective, 4, 5, 6 goes right to left, and this is an arrow pointed up. This carbon atom has flipped its orientation in both dimensions. It's as if we took carbon number 5 and flipped it like a pancake to get the arrow top to bottom, and then we flipped it again to get the arrow left to right. That does 2 flips, and that's going to bring the NH2 back into its dash notation in both the original molecule and in the new molecule. Another way of looking at this is we took the 4, 5, 6 group and we did a 180 degree steering wheel rotation to bring it into place in the new molecule. Because all it is a steering wheel rotation, the NH2 remains on a dash in both cases. The carbon number 6 group goes 5, 6, 7 left to right, and that is an arrow pointed up. In the new molecule, that arrow goes right to left and is an arrow pointed down. Just like carbon 5, this flips carbon 6 on both dimensions, bringing that chlorine group back onto the wedge in the new and in the original molecule. With only 3 carbons remaining, go ahead, pause the video here, see if you can work out how the wedge and dash notation should be for these 3 groups in the new molecule. Carbon number 7 starts out left to right as an arrow pointed down. It ends up right to left as an arrow pointed down. So this 2-carbon chain on carbon 7 will have its orientation flipped because one of those dimensions changes in the new orientation. Carbon number 8 goes left to right and is an arrow pointed up. Carbon number 8 in the new molecule also goes left to right and is also an arrow pointed up. Both dimensions are the same, so this sulfur group will stay on a dash in both the original and the new molecule. Finally, with carbon number 9, it starts out as a left to right arrow pointed down. It ends as a left to right arrow pointed down. All we're doing is moving this over like a steering wheel to bring it in place in the new molecule, and so this benzene ring will stay on a wedge in both the original molecule and the new molecule. Use pH as the abbreviation for the benzene ring in this molecule. With the arrow shift method, we track how that arrow shifts from the original molecule to the new molecule to make sure we get the wedge and dash in the right orientation.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.